terms of today's lesson, what we're going to be looking at is the quantum mechanical model of the atom. Okay. All right. This is a fairly complicated model. All right. And so one of the things that I will point out is that it can actually be really helpful to view this lesson as the recording later on and kind of go back over some of the finer sections, because there's just a lot of information here. But the other thing I'll point out is that while this model is very, very complicated, the way in which we actually address this is we look at it purely pretty much from a descriptive hand in terms of how we look at it. All right. And the main thing you need to be able to do is your SPDF notation. Okay. And the other thing you need to be able to do is be able to take that SPDF notation and turn that into a breakdown of where electrons will be found in the orbitals around the nucleus of an atom. Okay. The actual step for doing the two of those is actually really straightforward. There's just a few rules that are dressed up in fancy language that make it a bit harder to start and wrap your head around. But once you understand it, as long as you have a periodic table in front of you, you're golden, because it's really just using the periodic table as a map to write a little code that tells you exactly how many and where the electrons surrounding an atom are. Okay, so let's get into this, people. All right, so where we finished off not yesterday, in our last lesson on Thursday, is we took a look at the Bohr model. Super helpful, all right, and truly the beginning of quantum mechanics, in that what we had is we had the recognition, one, that we had electrons surrounding the nucleus. That was actually part of Rutherford's earlier model. Bohr was Rutherford's PhD student. Okay, and this model is sometimes called the Bohr-Rutherford model. All right, but Bohr came around and effectively pointed out that the electrons surrounding the nucleus are surrounding it at different energy levels, or another way of looking at that, different distances. Okay, and so that actually let him explain the spectrum that happens when hydrogen, or a hydrogen-like atom, is excited by running electricity through it, or making it become very, very high temperature, say throwing it in a fire. All right. Okay, and the spectral lines are actually the result of electrons dropping back down from the excited high energy state to the lower energy ground state, and that produces a very specific wavelength that is represented in the visual spectrum as that spectral line that acts kind of like a fingerprint for the element. It's part of the reason how we can look at things like stars and planets and galaxies in astronomy and work out what they're made out of. Okay, all right. But this also introduced us to another important concept, which was the idea that these electrons are sitting at specific, very, very specific energy levels. Okay, all right, which means that that's where quantum actually comes from, because quantum is a bit of a play on the word quantity. All right, and so what they found is they have, energy level 1, 2, 3, and 4, but there's no energy level 1.2 or 1.5. There's nothing in between. So that means the energy of those electrons are quantized. Okay, they exist at a very specific energy level. All right, and that, of course, is actually dependent on the number of protons that is found in the nucleus of the atom. Okay, now Bohr's model, as helpful as it was, it only really explained hydrogen. And while you could use it to actually explain what was going on with a lot of the elements in the periodic table, as soon as you hit the transition metals, it just started to fall apart. Okay, and of course that's not entirely unexpected. All right, in the case of Bohr's model, that model was never built to do that. It was just useful to actually explain a number of simple chemical concepts. All right, so over the course of the next 2 decades, what happened is we started to get more and more recognition that electrons are not particles, okay, per se. They're a wave and a particle at the same time. They're kind of a weird duality of things. Okay, and so Erwin Schrödinger actually started through the study of fundamental particles like electrons, actually proposed a new model for the atom. All right, using the idea of electrons existing as a wave. All right, and in this model, instead of thinking of the electrons as existing in a defined orbit, as a particle, they exist in a cloud surrounding the nucleus, and that cloud is the probability of where an electron might be found. And so it's a little bit of a different idea because you're not looking necessarily at an exact location of where an electron is. You're looking at the space in which where it can be, but it does let us actually look at the location of electrons using surrounding the nucleus of an atom using slightly more complicated language. And by using this slightly more complicated language, we're able to explain things like the emission of bigger elements with more than one electron. So we're already getting past what Bohr's model could do. There's actually a whole bunch of other things you can also explain from it as well. All right, now breaking this down, the main features of Schrödinger's atom, okay, is that we have the major energy levels that are surrounding the atom, and for historical regions, basically because we're building this on top of the Bohr model, we call them shells. All right, each of those energy levels actually contains separate energy levels of similar energy. They're called subshells. And this is where we start breaking down into the SPDF notation, and we start looking at the shape of the clouds that actually surround the nucleus of the atom. Now, each suborbital, or each orbital that it is found within a suborbital, can hold 2 electrons. Now, all the S-shaped orbitals, they only have a single orbital, which means they can fit 2 in there. The P-shaped orbitals have 3 orbitals, so you can fit up to 6 electrons. The D, which is where the transition metals start, have 5 orbitals, you can fit up to 10. And the F subshell, which is the lanthanides and actinides, they have 7 orbitals, which means you can fit up to 14 electrons. All right, and looking at this as well, our first energy shell around the nucleus, all right, only has a single S subshell, which means you can only fit 2 electrons in it. The second shell has an S and a P, all right, which means you can fit a maximum of 8 electrons, 2 in the 2S subshell, and 6 in the 2P subshell. And our third has both an S, P, and D subshell, all right, and so on. And so we start to actually basically build on top of Bohr's model, but start saying, hey, this is exactly where the electrons are at those energy levels. Okay, so this is just a different way of viewing it. This is a very helpful way of looking at it, just in terms of the table on the left just here. All right, we're organizing the electrons around our atom. We have our shells. There are major energy levels. We have our subshells. These tell us about where in the shell the electrons are actually found. And we have our orbitals. And each of our subshell is made up of a number of orbitals, and each orbital can have a maximum of 2 electrons in it. All right, of which those 2 electrons, like every single fundamental particle, they are actually spinning. All right, and there's 2 different ways they can spin. I'll expand on that in a little bit more detail in a second. But basically, they can spin up or down. I'm just going to throw annotate on just here. All right, the picture to the left is the orbitals surrounding an atom like carbon, for example. And this is where you can actually see in the middle. All right, so let me just our ball-like structure just here. Is the red showing up well on people's screens? I can change the color if we need to. All right, so the red, where I've just circled here, we have our S orbitals. That's a circular structure around the center of our nucleus. Okay, so we have our 1s orbital, then we have our 2s orbital packed around that. Then we have our p block orbitals. Okay, and each of our p block orbital, if we think of it as being like Cartesian coordinates, so we have y, we have x, and we have z. All right, each of these, I'm just going to change the color. Each of these, each electron basically occupies a region of space that is like a teardrop. And so a complete orbital looks a little bit like an hourglass. And when we pack each of them on top of each other, we end up with this structure that actually looks much nicer pitched to the right, but looks like our atom to the side just here. Now, if we were, I'm just going to just shut this for a second. If we were to take a look at the way in which these orbitals are found around the atom by looking at the periodic table, we can actually take a greater look at what all these s, p, d, and f orbitals actually look like in terms of their shape. Now, in terms of what you need to know as a Year 11 and Year 12 chemistry student, the shape of the s orbital, which is a circle, all right, and the shape of the p orbitals is as much as you need to know, okay, all right, in terms of being able to describe it, because you won't get asked a question to the level of where you would need to describe a d or an f orbital, but I am going to take a moment to show that to you. All right, so I'm just going to clear off these annotations, okay, and now I'm going to bring ptable up. Now, so ptable.com is the website I've gone to, all right, and I'm clicking on the orbital tab just here. All right, and so when we hover over each of these atoms found pictured just beside some notations, okay, we have the shape of the orbital, that's the orange ball, okay, and so when we have electrons in our 1s orbital, in the case of hydrogen and helium, they're shaped like a ball. We go down to our 2s orbital, and it's a little bit like a Russian egg. We've got a ball around a ball. All right, we come to our p orbitals for our next 6 electrons, and we can start to see the teardrops on those Cartesian coordinates. Okay, but when we get to, for example, our d orbitals, they start to get really crazy in terms of their shape. All right, and very, very complex to actually calculate. And likewise, here's a good one. So the outer shell of electrons surrounding neodymium is just weird. All right, now a big part of today's lesson is actually going to be about working with the SPDF notation and knowing how to actually read the type of notation that I've got highlighted on the screen just here, and how to take this notation and turn it into the notation that we use to label orbitals. Sounds very complicated. It's actually very simple, all right, in terms of the steps you're doing. You just need to know how to read it. Alrighty, so let me just fix up this so it's sitting nice on the full screen for us. Now, one of the things that we need to be mindful of is that there's actually quite a few rules in terms of how electrons sit around the nucleus. One of these, of course, is the Pauli exclusion principle, which states that every single orbital can only have 2 electrons in it. All right, now, of course, each suborbital might have more than one orbital, which is why we can pack lots and lots of electrons around the atom in our higher shells, because they have more than one suborbital. All right, but each orbital that is part of a subshell can only fit 2 electrons in it. Now, these electrons, because they are like everything that is a fundamental particle, neutrons, protons, electrons, even smaller subatomic particles that make them up, they all spin. In fact, it's kind of one of the interesting rules of the universe. No matter how big or how small you go, things tend to spin. All right, so you look at things like black holes, they spin. Galaxies, they spin. Subatomic particles, they spin. And because these particles, these electrons, they kind of act a little bit, and this is, it's not 100% accurate way of looking at it, but it's a helpful way when you first start to learn. They kind of act a little bit like a bar magnet, okay, in that if we were to sit them in an electric field, they're going to just generate, they themselves are going to have their own electromagnetic field. This has been drawn terribly surrounding them, and they'll have basically a north and south end. And so when you line them up in there, if you put an electron in a external magnetic field, what ends up happening is it'll spin one of two ways. All right, and basically what we consider this to be is it'll either line up with the field or it'll line up against the field. Okay, and that tends to come down to viewing it as have a half positive spin or a half negative spin, and we tend to look at that in terms of the orbitals in chemistry as being spin up or spin down. Okay, now when we represent this as a chemist in this model, usually what we do to represent an orbital, we draw a box. That's our orbital. And to represent our electrons, we just draw a kind of half arrow. So that's one electron, okay? And our second electron in that orbital will be drawn like this, all right? And so we have our spin up electron, we have our spin down electron. So it's something that has, a lot of complex language surrounding it, but in terms of what we're actually doing to represent that complex language is we have an up arrow and we have a down arrow. All right, so it's one of those sort of things that seems scary to start with, but when you actually get used to the way in which you represent these concepts, it's not that hard. Now, the second rule of Schrödinger's atom, which is called the AFBU Principle, all right, which I've probably murdered that dude's name, to be honest with you. All right, that is that the subshells that are closest to the nucleus have the lowest energy, and those that are further away have a higher energy. All right, and this principle, if we look at an atom that is in the ground state, and ground state means the lowest possible energy. All right, that means that the bottom subshells, they're going to, the orbitals found within them are going to be filled first. And so what that means, if we were to start plugging our electrons into a bunch of subshells surrounding a nucleus, you're going to start at the 1s. You're then going to go up to the 2s and the 2p subshell that are found in the second energy level, and so on. Okay. All right. And the other thing that's actually quite helpful to be aware of in terms of looking at this is you can actually start to see when you look at the energy of these subshells, you can see how they begin to overlap. You can see how, for example, your 3D subshell overlaps with the 4s and the 4p subshell. Okay, and that's where you start to get the backfilling happening in the Bohr model. All right, and we'll kind of look at that in a little bit more detail just here, and we'll talk about the couple of exceptions that come into play. All right, so we'll just take a little look here. What this means is, so far, we have the Pauli exclusion principle, which means each orbital can only have 2 electrons in it, so only 2, one going up, the other one going down. And then we have the AFBU principle, which says that the orbitals fill from the bottom subshell up at the lowest energy, unless the atom is excited in the first place and has extra energy put into it. Now, the next rule and it's the last rule, all right, and then we're going to be going into practice for how to use this model, is called Hund's rule. Okay. And what Hund's rule says is that each orbital within a subshell must have one electron in it first before a second electron can go into a subshell. Is that, so if we consider our 2p subshells just here, all right, this is the notation for carbon, by the way. All right, carbon has 2 electrons in the 2p subshell. Okay, it would be incorrect to throw those 2 electrons into the 1 subshell. That's not a low energy arrangement. As those electrons pack in, they're going to go into 1 subshell each. Now, if we go along to the next atom past carbon, what that means is that the extra electron it has is going to go in here. All right, and then of course, when we go to oxygen, which has another electron, all right, you're going to start to get a subshell. We'll have a second electron in it. Okay, all right, and then so forth. That'll continue to pack its way up. All right, now, the thing to take note is that you only get this doubled up subshell once every single one of these orbitals has 1 electron in it. Okay, that's the lowest energy arrangement. All right. The other thing, of course, that is worth noting is that when we talk about valence electrons, we mean those electrons that are found the furthest away from the nucleus. All right. And now, of course, since in this model, we can talk about where exactly in that energy shell those electrons are found, we can talk about what is happening in terms of an exchange, transfer, or sharing of electrons. All right, in a chemical reaction, we can talk about that using a lot more detail.